yesterday's lecture we talked about a linear controller where uk was given as minus L of xk, right. So, we have the system or the model which is xk plus 1 . This is a linear system, okay, and we have a linear controller which is okay. Now, the question is, how do we determine the controller gain L, okay, and L need not be a constant matrix. L could vary with time as well, okay. So, the one thing that we talked about was pole placement design. Okay, where you substitute uk in the above equation and you will get xk plus 1 equal to a minus bl times xk, okay. So, place the eigenvalues within a unit disk, okay. That is for stability, you can place them anywhere in the unit disk, okay. Question is where to place them, okay? And then there are different approaches in order to determine what that linear controller is going to be. One of that approach is the LQR. And that is based on minimizing a quadratic objective. And the quadratic objective is going to be min very similar to the objective function that you have seen in MPC. The difference that was there in MPC, that instead of this term you basically had delta u transpose r delta u, okay. Here instead of that you have u transpose r u, okay. And then there is a terminal cost term. The terminal cost may be different than this q or it may be same as this q. If q and qt are same, then that is the usual case, but the terminal cost need not be, this terminal weight matrix need not be same as the within the summation weight matrix, okay. The other difference is MPC came more from a practical viewpoint. So, that is why we said that within the summation itself Q and R could possibly vary, right. In the standard LQR you have Q and R remaining the constant matrices within the entire horizon. Okay. If P is equal to infinity, then you do not have this last term, and instead you have I equal to 0 to infinity, and that is called an infinite horizon objective. Okay. So, this is a finite horizon objective. Okay, an infinite horizon would be if P tends to infinity. This idea of LQR, the solution for LQR came in late 1950s, early 1960s. The idea of LQR had been around for a couple of decades prior to that. MPC on the other hand came about in late 1970s. So, you can see that MPC took some of the concepts from the idea of LQR, but implemented them in a very intuitive, from an industry perspective, practical way. Okay. So, if you remember the first lecture that I talked about the history of MPC, the reason for talking about history of MPC is so that all these various things that we do in this 12-week course, you should be able to place them, you know, appropriately how they come in. So, we started with the developments in late 70s, early 80s, okay, and the idea of LQR fed into MPC concept in late 80s and early 1990s. Okay. So, before we talk about how state space MPC would be done and what are the implications of that, we have been covering the linear control theory in the last 4 weeks, last 3 weeks. Okay. So, that is how we have paced our or organized this course. Okay. So, one way to do this is to set up and solve as we did in module 5. What did we do in module 5? In module 5, we had obtained well, I can put right. This is how we had obtained the stuff. Okay. Same way we will do this. Okay. So, what I want you to do is, let us define our matrix. Okay. What is this gonna be? Okay. You may want to try it out. It's not difficult at all. Done this multiple times. Okay. So, try to do this. Maybe we'll wait for maybe 5 minutes, and after that I will just show you what we are going to get. Okay. How is x1 related to x0 and u0? How is x2 related to x0, u0, u1? How is x3 related to x0, u0, u1, u2? That is what you need to find out. First row I will just populate for you. This is going to be identity matrix, okay, and 0, 0, 0, 0. Okay. This is what you should get. Again, same things that we have done before. Let us look at this objective function. It would be nice if there was a way to copy paste this, but yeah. Okay, we will write this objective function. Okay. Same fundas that we used in MPC part. This can be written as X transpose gamma x plus u transpose gamma u u. Why? Is because your x was, let us say p was 2, x0, x1, x2, okay. Let us say your gamma was q, q, qt, okay. Then x transpose gamma x, x is going to be x naught transpose q x naught plus x1 transpose q x1 plus x2 transpose qt. That is how it will be. Think back, assignment 1, you have kind of done the matrix combination and seen how it works, right. Yeah, I mean, if you want to see how it works, it is basically going to be x naught transpose, x1 transpose, x2 transpose. This is the x transpose part multiplied by q 0 0 0 q 0 0 0 qt multiplied by x naught, x1, x2, okay. This guy is a 1 by n, this is 1 by n, this is 1 by n, this is n by n, this is n by n, this is n by n. So, this multiplication will result in q x naught, okay. Next is going to be q x1, q, oops, no, x naught transpose q, x1 transpose q, x2 transpose qt multiplied by x naught, x1, x2, which is x naught transpose q x naught plus x1 transpose q x1 plus x2 transpose qt x2, which is what you had in the objective function. Okay. Again, not very clear, sit down, make a 2-dimensional x, right, make x as point, I mean take up your quiz question itself, right. You arbitrarily you make up your x, x1, x2, x3, okay, do the actual summation and then do this matrix way and see that you are going to get the exact same result. You can literally, you can try this out and it will work, yeah. X minus 0, that is the objective over here. In MPC, the objective was set point tracking, disturbance rejection or regulation, all 3 objective functions. LQR, the objective is only regulation, okay. Next module, we will talk about, or maybe next module, we will talk about how to handle disturbance rejection and how to handle set point tracking, okay. Easy way to handle it, you augment your state. So, your state Z will be XR or Z will be XDR, where X is the state, D is disturbance, R is set point, okay. We'll come to that. Okay, clear? So, this is how this works. Regulation means starting with any arbitrary xk, starting with any arbitrary x0, you determine the control action so that the system goes to origin in finite amount of time. That is the question that controllability reachability answers, whether or not you can. LQR tells you what is the best way to do this in a quadratic sense, what is the best input moves so that you get the system from x naught to origin such that this particular objective that I have shown you, the quadratic objective function, is minimized. Okay. So, this is your objective function and you can kind of just work this out. X is nothing but Sx x naught plus Su capital U transpose gamma x okay, as we had done earlier. This will be U transpose SU transpose gamma x SU U plus x naught transpose Sx transpose gamma x Sx x naught plus 2 times Sx x naught transpose Sx transpose gamma x Su U, right. I'm able to do that because I've done this multiple times, but it's not difficult at all. It's just A plus B multiplied by Q multiplied by A plus B. So that's going to be A Q A B Q B 2 times A Q B, that's what it is. Okay. This is our Hessian. This is our gradient. Okay. Yep, I forgot. Thank you. Right, it is U transpose H U plus 2 times G transpose U. So, G is SU transpose gamma x Sx x naught, and that is what I have written there. SU transpose gamma x Sx x naught. Okay. Sorry, I forgot the negative sign. Okay. This guy is nothing but our big L. And that is essentially how you can actually do LQR. Nobody will do LQR this way. Why? Because it is extremely expensive computationally to calculate LQR this way. Okay. And the big breakthrough was again due to Kalman. He used what is known as the Bellman principle in order to have a recursive computation of L. Okay. Now, if you substitute the L that you get over here into this equation, okay, you will basically see that your objective function is a quadratic function of x naught. Okay. So, the objective function, let us call it V, P horizon objective function, okay, is going to be x naught transpose some S multiplied by x naught, okay. And these are two important results. Okay. So, to summarize, linear model, okay. This is essentially what we have done. We will pick up from here tomorrow.